Hi there! This series covers the first 100 Project Euler problems to help you learn how to solve unfamiliar problems. Project Euler presents complex math challenges to be solved with programs running in under a minute. Although they prohibit sharing solutions, the first 100 problems can be shared for instructional purposes. I encourage you to attempt each problem on your own before watching the corresponding video. I am currently learning Python and have been doing so since mid-January. I have no professional experience in the language and have only completed the Python for Programmers course on Execute Program. While I'm learning quickly, I don't claim any real expertise. Today, we're looking at the 71st Project Euler problem. As always, I will link to both the problem and my repository in the description. Let's dive in. Problem 71. Ordered fractions. Consider the fraction n over d, where n and d are positive integers. If n less than d, and I think HCF means highest common factor of n and d is 1, it is called a reduced proper fraction. If we list the set of reduced proper fractions for d less than or equal to 8, in ascending order of size, we get all of that. It can be seen that 2 over 5 is the fraction immediately to the left of 3 over 7. By listing the set of reduced proper fractions for d less than or equal to 1,000,000 in ascending order of size, find the numerator of the fraction immediately to the left of 3 over 7. Okay, so something to notice here is we don't actually need to list all of these fractions. We just need to figure out which fraction is the closest to 3 over 7 without being over 3 over 7. So let's copy this from here again. Create our new little file. Okay. So first we grab our from date time lines that I just love so much. Apparently. Okay, so our limit is equal to 1,000,000. And let's see. Okay, so that should give us that. And I'm hoping that the number of decimal points isn't a big deal. So let's see. Numerator equals... I'm just going to say 2 and 5. So we can be pretty confident that 2/5 isn't going to be the correct answer. The correct answer is going to be some fraction between 2/5 and 3/7. So I'm just starting it off here. And then at the end, we'll do pound So we'll print it out like that. So right now, it would just print 2/5, obviously. So we have to add some actual logic here. And what I'm going to say is for D in range, I'm going to start with 2 because 1 over 1 is just 1. And go up to the limit. So, and then for n in range, 1 to D, if n divided by D is greater than target, then break. So in other words, we get to the point where n divided by D is more than 3/7, then we've gone to the right of 3/7. So we don't actually want to continue. And then otherwise, if it's just greater than numerator over denominator, then we have to check whether it is a reduced proper fraction. So now I am going to say for I in range 2 to the max, or rather 2 to D, I'm just going to say is reduce equals true. And then for I in range 2 to D, if D mod I equals 0 and N mod I equals 0. Actually, this should only go to N, not to D, because it's not a factor of... If it's larger than D than N, then it can't be a factor of N. It's false. Break. If it is reduced, numerator set numerator equal to N, and denominator equal to D. Now, what you'll notice here is I have a triply nested for loop. I don't know for certain that this will be efficient enough. But let's actually take our limit down to, what is it, 8? Just to make sure that we do get the 2/5. Oh. That clearly needs to be an equal sign, huh? Okay. So, for a limit of 8, it just worked. For a limit of 1 million, it's going to take some time to process through all of these numbers. I'm not sure exactly how much time, since it's effectively going to be limit squared. Okay, so I'm thinking that this is probably not going to be efficient enough for what we need here. And it could be more efficient if instead of doing this, I did, well, A. This will make it slightly more efficient. Well, maybe more than slightly, because it'll cut out all of these. I just kind of want to let it run to see how long it does take, but I might get impatient here in a little bit. Let's see. Yeah. Okay, so go ahead and crash that, run it through again. Actually, before I do that, I'm just gonna throw in a if d mod 1000 is 0, print actually, let's make this 10,000, because I don't want it to print out 1,000 times. I don't really want it to print out 100 times either, but right now I'm just kind of trying to see how long it takes to get through even the first. Okay, so the first 10,000 didn't take super long, but the subsequent ones will take longer and longer because of D getting bigger and bigger. Okay. I'm gonna go ahead and throw this here. And bump that up to 100,000 and see exactly how long it takes to get through the first 100,000. Why 100,000? Because then it only needs to go through 10 times. Okay, so here actually, this is pretty inefficient. I don't know if this is where the inefficiency is necessarily, but this could be more efficient because we're going through 2 and then we're going through 4. Really, this should only go through the primes that are less than n divided by 2. So let's go ahead and do some prime calculations. I'm just going to steal that from here. And this is that sieve method that I've done in many of my other videos, where we basically just go through for the prime, go through the numbers and set to true any index that is prime. So then I can make a primes array. And I'm going to try to do this in one line using a list comprehension. So for I in range 0, or rather, length of is prime, if is prime of I equals true. I think that'll do it. And then I am going to say for key in primes, if key is greater than n, then we break. Otherwise, if it is a factor of both the denominator and the numerator, then it is not a reduced fraction and we break. Okay, so that should make us somewhat more efficient. Let's see how quickly we get through the first 100,000 with that method. As you can tell, we did not get through even the first 100,000 with this other one, and it was going for about 4 minutes, looks like. So, not wonderful. And I think there's going to still be a better way of doing this. And it's just not coming to mind right this second. Obviously, since we did not get the answer immediately, and I think it's even been going for almost a minute now, this isn't going to be efficient enough to meet our minute time limit that Project Euler gives us. So... Huh. Something has just occurred to me, which is I don't even need to check all of this. Let me see if I can do this. Let's just not even bother with all of this prime stuff. And see if that makes this significantly faster. Okay, so I am also going to add a break statement here. Not having all of this check, it might make it so that we get the incorrect answer, but it should also make us a lot faster, so let's just see what answer we get. Okay. So maybe not fast enough still. Because here's the thing, a properly reduced fraction is going to be what we find first. So, like, 2 over 5. The next fraction that is equal to 2 over 5 is going to be 4 over 10. But 4 over 10 would be equal to this, not greater than it. So I don't think we need to even calculate the reduced ones. And possibly we could make this slightly more efficient by calculating that once instead of twice. But I don't think that's going to be our major slowdown here. I think our major slowdown is not being clever enough with looking through the ends. So what we actually want to do is look at the ends that are relatively prime to D instead of just any of them. But calculating all of the relative primes is also difficult to do efficiently. So, still going. It's been like 4 minutes when we haven't gotten through the first 100,000. So, obviously, we're not going to get through a million of these with anything like efficiency. Um, I was really hoping that this would prove to be much more efficient, even though we're basically going through so many combinations because we're doing so little with them. But um, it doesn't appear to be the case. So what is a better way to calculate the starting point for n? And I think it would be, so 2 over 5, right, is 0.4. 2 over 5 is 0.4. So so let's see, if you multiply 5 times 0.4, you get 2. So in order to find the best n to start with, I think that it's going to be d times numerator divided by denominator. Okay, so it took 6 minutes and change, but it did go through the first however many that is. So I'm going to say start is equal to the int of b times the fraction. And that should cut down our time significantly, especially as we start getting to these higher numbers. So let's say when d gets to equal to 6, 6 times 0.4 would be 6 times 0.4 would be like 2.4. The int of that would be 2. But when we get up to like d equal to 100, instead of starting all the way at 1, we would be starting like, just for the sake of argument, let's say we're still, the minimum is 2/5. Then we would be starting at, so for the number 100 times 0.4, we would be starting at 40 instead of 1, saving us a significant number of loops. And then I think, well, this could be n divided by 2, but frankly, this is going to catch that and fix it anyway. So let's stop that and see if we can get through the first 100,000 much faster. That worked. Okay, so found fraction immediately to the left of 3 over 7 to be this over this. And I am actually going to put all of that in our end statement. Delete our little thing here. And we can see these numbers are very, very close, but this one is smaller. So I just did that so I could visually do a double check. So let's take this 428,570 and see if it is the correct answer. I have a feeling it will be. The only thing that we're not checking is whether it is a properly reduced fraction. But as I already explained, I don't think that will be necessary because I think the first one that comes up is going to be properly reduced. So let's find out if I'm correct. Oh. Well. Sometimes I should refresh the page before I start recording, right? And that is the correct answer. All right. So, again, we did not need to check whether it was reduced. because by the time we got to like 4 over 10, f would have been equivalent to that. And actually here we can do just fraction instead. And obviously we're going well under our minute-long time limit here. We need to calculate primes. Actually, no, I want to leave that up there. Okay. So, all we're doing is we're saying, okay, so for every d in this range, start is going to be d times whatever fraction, but convert that to an int, should be flooring it. So, like, if the answer for this is 2.4, this should be 2. And then calculate the decimal equivalent of the fraction. And then if it is larger than or equal to our target, we just break out of the loop, go to the next denominator. Otherwise, if it is larger than our current fraction that is immediately to the left of 3/7, we reset our current values. And yeah, I'm going to call it there for this one. As a reminder, if you would like my help with any code challenge you are working on, please check the link in my description, and I'll catch you in the next one.